higher derivative. Oh, here it is. Okay, okay. Hello, everybody. This is Professor Ma, and this is the introduction to the sections on higher derivatives. And these are the two objectives we have: the notation for the higher derivatives, and some observations on the higher derivatives of different families of formulas. Okay. So we start out with simple function x squared, and its first derivative is 2x. And if we take derivative again, then so we do it like that, and that derivative will be 2. And the second derivative, so we will write this with a double prime consecutively, or we write it as a power with the parentheses denote as its derivative. That's great. And so, and second derivative, notice is 2, and the third derivative, notice is 0. Okay, and so third derivative will be noted like this. And in general, the nth derivatives we noted in this fashion, kind of like n to the power with the parentheses. The dx notations is noted in like in these manners. Okay, so here are some examples. Here are the first 5 derivatives of the polynomial. Here is a 4th degree polynomial. So here's the first derivative. Second one, power comes down. Third one, 48x minus 6. Fourth derivative will be a constant, 48. And the fifth derivative will be 0. Okay. And so in general, you have a Lagrange polynomial. If you take a derivative, the power gets subtracted by 1. So you have an nth degree polynomial. You will do n times the derivatives, then you wind up with the zeros. And if you do it 1 more times, you wind up with if you do n times, you wind up with a constant. If you do m plus 1 time, for sure you get 0. Okay, so first is these big important observations about derivatives of polynomials. That is, if I keep taking them, eventually they're 0. More precisely, you take it 1 more times than the power of the polynomials, and then it will be 0. Okay. Now, how about fractional functions like this? Well, for all the other powers, they don't become 0. They get, in some sense, messier and messier because you're going to subtract the power by 1. So it's the first derivative is like this to the it's over x to the 1/3 power. Then the second derivative x to the 4th powers in the denominator, and so on. So okay, so they don't get cleaned up. They don't get become 0, very like the polynomials. Okay. How about log of x? Well, the interesting thing about log of x is its derivatives becomes an algebraic functions. Derivative of log of x is 1 over x. So if I take it again, then it will be another algebraic function, 1 over x squared, negative of that, and so on. So the derivative of log of x actually jump over to a different families. Okay. In general, if I take the formulas for log of x, if I take the argument to be a polynomial, then the derivative will be the derivative of log of u using the chain rule is u prime over u. Oops, u. And u prime is another polynomial in this case. And so, in other words, the derivatives of a polynomials, of log of a polynomials, turns out to be a rational functions. If I keep taking derivative again, the derivative of rational functions is itself the rational function. Why? Think of the quotient rule. There's no other different type of formula comes in. So And so from here on, derivative of a higher derivative of a log of a polynomial, they all become rational functions. Okay. How about trig functions? Trig functions goes in cycles. Derivative of sine of x become cosine, and then second derivative is minus sine, the third derivative is minus cosine, and the fourth derivative, it goes back to itself. So it goes, it's like going around a clock. We only 4 hours, 1, 2, 3, 4, and a cycle of 4. And you can look at the cycles and decide which, for a higher power derivative. For instance, if I want to take the derivative of sine of x, say to take a derivative 103 times, well, that's easy because the sine of x. Take the derivative 100 times. Okay, and then take 3 times more. Well, if I take it 100 times, it comes back to itself. So in other words, this is the same as the sine taken derivative 3 times, which of course is minus cosine x. Okay. So, and similar for cosine, it goes in cycles, like sine. Now I want to point out the derivative of tangent secant squared, the derivative of secant tangent secant. So between tangent and secant, if I keep taking derivatives, I wind up with a bunch of other tangent and secants multiplying. So we finish with the polynomials in tangent and secant. So same thing with cosecant and cotangent. Okay, so we're summarizing the end over there for those two families. Finally, if your formula has a exponential factors, okay, like e to the u of x times some other formulas, then when we use product rule on these, and because the derivative of e to the u has itself in it, using the chain rule, so we find out that that factor e to the u comes back. In other words, I can pull out e to the u, and what I wind up is the derivatives of some formulas with e to the u of x. I wind up with another formula with e to the ux in it. It doesn't disappear. It doesn't change into anything else. It will pop up in the derivatives. And so means if you keep taking higher derivative, it will keep popping up. Okay. So derivative of e to the ux and bx is another function of the form e to the ux times some other formulas. Okay. And that things left over when we talk about e to the ux, derivative of e to the ux, and what we have is these portions. It turns out this part is important in differential equation for one to recognize or use this fact that it's a spin-off from the derivative of e to the ux. And that's it. Okay, the last is the summary of what we just went through of the higher derivatives of different families and derivative families of algebraic stay within algebraic. The derivative log of algebraic jumps into algebraic families. Derivative with e to the ux as a factors, that e to the ux will persist. And derivative of sine, cosine, cycles, among them. So derivative of tangent and secant are polynomials in tangent and secant. Keep taking it still more tangent, more secant, multiplied with everything. And similar things between cotangent and cosecant. So this is the summary of the higher derivatives, and that's it. Bye bye. Have a good day.